Welcome. In this video we're going to talk through some titration problems from page 16. And if we look at this first problem right here, we're talking about the titration of a weak base, and we're asked what will be the pH of the mixture at equivalence. And it might be helpful to write out the reaction here. We don't have the chemical formula for aniline. We do know that it is a weak base. Let's just use the generic B for base. And when we have a titration of a weak base with a strong acid, we know the reaction is going to look like this. So notice how if this is a weak base, after the reaction is done, you're going to produce the conjugate acid, which will also be weak, because weak pairs with weak, and strong pairs with neutral. So we should find that through these acid-base neutralization, you're going to end up making the conjugate of whatever you started with. So when you titrate a weak base, at the end of the reaction, you'll end up with a conjugate weak acid. If you start with a weak acid, you're going to end up with a conjugate weak base at the end. And at equivalence, that means that you have pure product. So since our product is a weak acid, the pH is going to be below 7. And that is because our solution is going to be made of BH+, which is the conjugate weak acid. And I've seen many students explain this saying, well, the pH is going to be below 7 because you're adding a strong acid. But that doesn't really explain what is happening, because at equivalence, you were not going to have any strong acid in the solution anymore. Equivalence means all your reactants have gotten used up and all you have is products. So you have to think about the pH at equivalence in terms of what your products of this reaction are. And at this point, at equivalence, you only have this weak acid. There's no strong acid left, there's no weak base left, they've all gotten used up, and you have pure products at equivalence. When you're choosing an indicator, you want an indicator that will change color at the equivalence point. And we just said here our equivalence point is going to be somewhere below 7 because our product is acidic. And the pKa of an indicator indicates the pH at which it changes color. And this can be kind of confusing because indicators are themselves acids, so they have pKa values, but your weak acid you're titrating has a pKa value as well, so you have to make sure we keep those straight. So the pK of the indicator should match the pH at equivalence. So the pH at equivalence is going to be below 7, so I'm going to want to choose an indicator that changes color in the acidic range. So in this case, erythrocene would be a good choice. Looking at a problem like 2009, this is actually a throwback to Unit 3. This is just a stoichiometry reaction problem. So you're doing a titration of an acid and a base. We did this a few times again back in Unit 3. We did a titration of peroxide. That was a redox titration. We did a titration of sulfuric acid. We did one with conductivity as well, with barium hydroxide and sulfuric acid. So we want to look back at some Unit 3 things. But considering what's happening here, let's write out the molecular equation first. So the molecular reaction is you're mixing together barium hydroxide and HOBr. This is a double displacement reaction, so you're going to make barium OBr2, and you're going to make H2O. And it looks like in order to balance this out, you're going to need to have a 2 and a 2 here. So this is our molecular equation. If we're looking at the net ionic equation, we could just look at it this way. We could say we're reacting together hydroxide and OBr. This is our net ionic equation happening between our strong base and our weak acid. And in a stoichiometry problem, your first step is always going to be to find moles. So whenever you're dealing with solutions, you want to go back to this idea that molarity is moles per liter. So to find moles, I'm going to take my molarity times my liters. So you want to say, what do I know? Which thing do I know the molarity and the volume of? And this case, it looks like HOBr is my given. So you can take your molarity of HOBr, which is 1.46, times the volume in liters, and that will give you your moles of HOBr, which ends up being 0.0095 moles of HOBr. And then the next step in a stoichiometry problem is to use your mole ratio. And here's where it's helpful to look at the molecular equation rather than the net ionic equation, because I'm not trying to find moles hydroxide, I'm trying to find moles barium hydroxide. So the top equation is actually the one that's more useful to me right now. So for every 2 moles of HOBr, I need 1 mole of barium hydroxide. So that will give me moles barium hydroxide. And then I want to find volume of barium hydroxide. So again, I'm going to use this equation, moles equals molarity divided by liters. The answer to here was 0.0047 moles. So if I plug this here into the moles value, and I know the molarity is 0.115, I should be able to rearrange and solve for volume. And you end up getting a volume that is 0.041 liters, which is 41 milliliters. So this is a stoichiometry problem. Part B, it has to do with what we talked about in the first problem as well, where you're thinking about what is going to be present in the solution at the equivalence point. So if you look up here at your net ionic equation, the products of the reaction are OBr minus and water. So at the equivalence point, I'm just going to have OBr minus present in your solution. And since HOBr is a weak acid, that means OBr minus is its weak conjugate base. So in this case, the pH is going to be greater than 7 because at equivalence I have this weak base in the solution. If we look down here at problem 3, we are looking at a weak base strong acid titration. So remember, the weak base strong acid titrations are the ones that don't really follow our double displacement pattern. They look more like a combination reaction. So your weak base is just going to be a hydrogen taker, and it's going to grab that hydrogen and form the conjugate acid. And then part B asks us to sketch the titration curve. And notice how it says from 2000. This is from an old AP exam. So some things that you want to look for in this curve. They're looking for, and I've got some notes here on what they were looking for in the AP exam. So they're looking for the initial pH to be high. You didn't have to calculate what it was exactly, but if you did, it would be somewhere around a pH of 10. You want to show that the equivalence point is around 15 milliliters. And the reason why you know that is because the equivalence point is the point at which your moles are equal, and where you've added an equal number of moles of your acid and your base. And it looks like your moles of base, you can find moles of base by taking molarity times volume. So 0.1 molar and 0.03 liters. We've got 0.003 moles of NH3. So at the equivalence point, you want that number of moles of H+. So if you want, let's rearrange this. Mole equals molar per liter. If you want 0.003 moles of HCl and the molarity of HCl is 0.20, you should be able to rearrange and solve for volume. So liters is 0.003 divided by 0.2, which ends up giving you 0.015, I believe. The other way you can think about it is, you notice that your acid is twice as concentrated as your base. So in order to get to the equivalence point, you need to add half as much acid as you had base. So if you had 30 mils of base and it's 0.1 molar, you're going to only need 15 mils of 0.2 molar to get to a point where you have equal moles. So that's what we're looking for there. So you're going to hit equivalence right here. And at equivalence, we know it's going to be acidic. So you want the pH at equivalence to be somewhere in the acidic range, so like right around here. And then so our graph is going to maybe look a little bit like this, and then it's going to drop down here lower. So that's what you want your graph to look like. The indicator that's going to be appropriate, we want an indicator that is going to change color at the equivalence point, which is going to be somewhere below 7. And so the only indicator that's doing that of the options they gave us is methyl red. So that's the indicator I'm going to choose there. And then looking at part D, I've got equal volumes of NH3 and NH4. Is the resulting solution acidic, neutral, or basic? Well, I have to think about what is going to be in my solution, and it's important to recognize that NH4Cl is an ionic compound. So I'm going to break it apart into its ions. And when I do that, if I write down these things that are in my solution, hopefully I notice that, hey, I've got NH3 and NH4. That looks like a weak acid and its conjugate base. That is a buffer. Okay. And we know that for a buffer, the pH is going to be close to the pKa. They're not asking me to calculate what it is exactly. Actually, in this solution, we know they're actually both 0.1 molar. So if we look at our Henderson-Hasselbalch equation, pH equals pKa plus log A over HA, if you plug in two numbers that are the same, like here 0.1 divided by 0.1, you will find that the log of this value is 0. So in this case, the pH is actually exactly equal to the pKa. So in order to find the pH of this solution, you would need to know the pKa. And notice you're only given a Kb. So to find the Ka, you would do this equation, Ka times Kb equals Kw. So what that means is the Ka for NH4 times the Kb for NH3 is going to be equal to 10 to the negative 14. And you should be able to find the Ka. And again, we don't have to be specific, so you don't actually have to find the exact number. You could even just kind of eyeball it. We should be noticing that the Ka and Kb exponents tend to add up to 15. So if Kb is around 10 to the negative 5th, I can just eyeball this and say, oh, the Ka is going to be around 10 to the negative 10th. We don't need to know exactly what it is. We just need to know if it's acidic or basic. And then I should be able to estimate what the pKa is based on this number right here. So if this number is a 10, then my pKa is going to be around 9 or 10. It ends up being close to that number. And that means the pH is going to be around 9 or 10. So my solution is going to have a basic pH in this case. So you don't even really have to use your calculator. The idea is you can just kind of eyeball it with these ones. Estimate. So here's another one. We are titrating a weak acid. The other one was titrating a weak base. So it might help to write out this reaction. So I've got my weak acid HX. I'm adding a strong base to it. I make X minus and water. And you're going to sketch the titration curve showing the pH changes that occur. Clearly label the equivalence point. So it tells us here the equivalence point is reached when 25 mils of NaOH has been added. So I know it's going to happen right here. Okay, so that's my equivalence point. And at equivalence, I'm going to have only product. So at equivalence, I'm going to have only X minus in the solution, and X minus is a weak base. And I know that because they tell us that HX is a weak acid, and the conjugate of a weak acid will be a weak base. So weak pairs with weak, strong pairs with neutral. So right now, let's see, I'm starting out with a weak acid, so the pH is going to start low. So let's pick something down here. It's going to start low. And at the equivalence point, which they tell us is 25 mils, the pH should be somewhere above 7, which I'm going to choose right up here. And then our graph is going to look a little bit like this, boom, and then it will level off up here. And they asked us to label the equivalence point, so I'm going to stop and label that. And it says, describe how the value of the acid dissociation constant Ka could be determined from the titration curve. So this is where we get to use the fact that when we're looking at a titration, this area in the middle is the buffer zone, where you have a mix of HX and X minus. And if you're exactly at the halfway point, which in this case, since equivalence is at 25 mils, that means that right here at 12.5 mils, at the half equivalence point, the amount of HX and X minus are equal to each other. So at this half equivalence point, pH equals the pKa. So you could find the pKa by looking at the graph. So it looks like here my pKa is about 5. Let's just estimate it. I know I was just sketching that graph. The pKa is the negative log of the Ka. So to solve for Ka, we would go 10 to the negative 5th. And we have just estimated what the Ka of my weak acid is. And here is a titration showing a diprotic acid. And it's saying what is present at letter A on the curve. So it might help to kind of like stop and figure out what's present at all points of the solution. So initially you've got all H2Y, and we've got two reactions that will happen. So you add a hydroxide. First we're going to remove the first hydrogen from my diprotic acid, and this is going to be what's present in solution at the first equivalence point. So right here you're going to have pure HY minus. And then when that reaction's all done, if you keep adding hydroxide, you're going to lose the second hydrogen and make Y2 minus. So this is what is going to be present at the second equivalence point. So what is present at point A in the solution is Y2 minus. All right, well, thank you for listening. I hope that helped.